Welcome to the deep dive. Today, we're tackling something pretty technical, the kind of stuff usually buried deep in manuals and courses. Our mission: to take an instructional guide on the Canadian Electrical Code, the 2025 edition, and we'll pull out the absolute must-know info for you. Now, why bother digging into the CE code like this? Because getting conductor and conduit sizes right is, as our sources put it, an essential part of the electrician's daily work. I mean, get it wrong.
Oh, absolutely. Get it wrong, and you could be looking at failed inspections, dangerous overheating, maybe even big efficiency losses down the line. So for you, the learner, we're really zeroing in on the rules for circuits 750 volts or less. We're drilling down into ampacity, that's section 4, sizing the neutral, and also voltage drop, which is crucial for performance. That's sections 8 and 12.
Okay.
The main goal here is to help you figure out acceptable conductor and conduit sizes quickly, accurately, and hopefully without getting totally lost in the weeds of the code.
Right, cutting through the noise. So let's unpack this. We'll start with a big one: managing heat, ampacity. Okay, so when you're picking a conductor, the code basically lays out 5 key things you have to satisfy, like a safety checklist. First off, you need the minimum ampacity for whatever load you're running. Makes sense. Second, is the load continuous, running for hours, or is it more on and off? That matters. Third, and this is really important, the max conductor termination temperature, where it connects. Fourth, figuring out the conductor's actual ampacity, considering its environment. And fifth, those specific conditions, like how hot the area is it in a raceway, things like that.
You nailed it. And that third point, the termination temperature, that's often the biggest limiting factor. It's all about protecting the connection points, the weakest link, really. See, the current listed in those key tables 1 to 4, that's the maximum current that'll make the conductor hit that specific temperature.
Okay. So you can't just pick the highest rating the wire itself can handle.
Exactly. You have to look at the lowest temperature rating of any piece of equipment that conductor connects to. Usually that's 75 degrees C or maybe 60 degrees C. And if the equipment doesn't actually list a rating, the code has defaults.
Right.
It's 60 degrees C for equipment 100 amps or less, or if you're using wire size number 1 AWG or smaller. And it bumps up to 75 degrees C for gear over 100 amps or for conductors bigger than number 1 AWG.
Okay, but here's something I found really interesting. Rule 4006, sub-rule 4. It says this strict temperature limit, it only applies to the first 1.2 meters of the wire, about 4 feet.
That's right. It's a crucial detail.
Wait, so does that mean if I have a long run, say 100 meters, I only need to worry about that first bit being the thermal bottleneck?
Precisely.
That seems huge for design. You could potentially run the rest of the conductor at a higher ampacity if the ends allow for it.
You absolutely could, assuming other factors like voltage drop don't become the limit instead. That first 1.2 meters is the safety check on the equipment. Once you move past that point, then you start worrying more about the environment the conductor is running through. The code treats heat like a fever for the wire.
And you have to treat it by limiting its workload, basically.
That's a good way to put it. Heat dissipation is just massive. Running single conductors out in free air, that's the easiest way for them to cool off. Use tables 1 and 3 for that, but stick them in a really hot area, say above 30 degrees C ambient, and they just can't shed heat as well.
Right.
So if you've got 75-degree rated conductors in a space that's hitting 45 degrees C, you've got to go to Table 5A and apply a correction factor.
And for that specific example,
it's a factor of 0.82. You multiply the conductor's base ampacity by 0.82, disrating it.
And those disrating factors can pile up, can't they? Table 5A is for the heat around the cable. But what about the heat inside a bundle of cables?
Yeah, they definitely stack. If you pack 4 or more current-carrying conductors into a single raceway or cable, well, they all heat each other up. Their ability to cool down just plummets. So then you need another correction factor, this time from Table 5C.
Wow.
So you might end up needing a much bigger, more expensive wire size just to handle a moderate load safely, all because of bundling and maybe a hot environment. It's this constant battle against heat buildup. Speaking of bundles, let's talk about counting which conductors actually count towards that D rating. It sounds simple, but it can be surprisingly tricky.
Okay.
Generally, the neutral conductor, it's usually just carrying unbalanced current. So Rule 4004, sub-rule 3, says you don't count it for D rating purposes. Most of the time.
Most of the time. There's always a catch, isn't there? So what's the exception? When do we count the neutral?
The big one involves 3-phase, 4-wire systems. If you take a 3-wire circuit off that kind of system, the common neutral wire in that circuit, it ends up carrying about the same amount of current as the phase conductors.
Really?
Yeah. So in that specific setup, The neutral must be counted as a current carrying conductor for debar rating.
Good to know. And just to be clear, bonding conductors, the green wires are grounds that are never counted,
They
right?
never counted for debar rating, no. And another interesting point, the code often waives those derating factors for the short bits of wire inside electrical equipment, like where they terminate inside a big panel board.
Why do they get a pass there? Seems like a hotspot.
You'd think so, but it's actually about better heat dissipation. The sources say the larger space, the bigger cross-sectional area inside that equipment, allows for more air movement, better cooling.
Makes sense. Rule 40047A, right?
That's why.
Okay, let's shift gears. What about really big loads, like, say, 737 amps? You're not pulling one gigantic stiff piece of copper for that, are you? That sounds awful to install.
Generally not, no. It's often way more practical and sometimes cheaper to run multiple smaller conductors in parallel instead.
Right, parallel runs. But there are rules for that too, I assume.
Oh yes. Rule 12-108 lays it out. Critically, the smallest size you're allowed to use for ungrounded conductors in a parallel set is NAWA 10 AWG. Can't go smaller than that.
1/0 minimum. Got it. And installation matters here too, right? You can't just run all the phase A wires in one pipe and phase B in another.
Absolutely not. That's where the physics gets demanding, like you said, to make sure the current divides up equally between the parallel runs and also to balance out the magnetic fields. You have to install one conductor from each phase, plus the neutral if there is one, together in each conduit or raceway. Keep the phases grouped.
Okay. It's like trying to drink equally from 3 straws. If they aren't bundled together properly, one might draw way more than the others.
That's a perfect analogy. If you don't keep that balance, the impedance won't match and the current won't share nicely at all. And speaking of magnetic fields, that leads us to another tricky issue. Single conductor metal sheathed cables. Things like RA90 or tech cable used as single conductors.
Okay, what's the problem there?
Well, AC current creates that constantly expanding and collapsing magnetic field around the wire. With a single conductor inside a metal sheath or armor, that field actually induces a voltage in the metal sheath itself.
Whoa. So the magnetic field can basically turn the cable's own armor into a source of current.
Pretty much. It can cause these circulating currents, often called sheath currents, to flow in the armor or sheath.
And that's bad because
Those currents generate heat, extra heat, right in the sheath that the conductor wasn't designed for. It can damage the insulation over time, potentially leading to failure.
Yikes. Okay, so how does the code deal with that? Rule 4-08, right?
Rule 40081 gives you 2 main options. Option 1 is simple but costly. Just accept it's going to happen and derate the conductor's ampacity way down to 70% of its normal value.
Ouch, a 30% hit. What's option 2?
Option 2 is to design the installation to eliminate those sheath currents. The most common way is to bond the metallic sheaths together and ground them, but only at the supply end of the run.
Only at one end. Why not both?
Because if you bond and ground both ends, you create a nice closed loop for those induced currents to flow through easily. You basically turn your conduit or sheath into a big, inefficient, and potentially dangerous heater. One end bonding breaks the circuit for those currents.
Okay, so we've wrestled with heat and ampacity. Let's zoom in on the neutral conductor now. Its job is to handle the unbalanced load between the phases.
Correct. And for larger services, typically commercial or industrial, if your maximum calculated unbalanced load is more than 200 amps, you don't necessarily need to size the neutral for that full amount. You size it for the first 200 amps, 100%. But for the portion of the unbalanced load over 200 amps, you can apply a demand factor of 70%.
So if the unbalanced load was, say, 300 amps,
Huh.
you'd calculate the neutral size based on 200 amps plus 70% of the extra 100 amps. So 200 plus 70 yields 270 amps.
Exactly. It can sometimes let you use a slightly smaller, cheaper neutral conductor on big feeders or services.
But I sense another but coming. There must be a catch.
There is a very important one. The 70% reduction, you cannot apply it to the portion of the load that consists of 2 specific things. 1, electric discharge lighting, like fluorescent or HID. 2, and this is increasingly common, nonlinear loads, especially on 3-phase 4-wire systems.
Nonlinear loads. Okay, that's things like computers, servers, modern LED drivers, variable frequency drives for motors, Basically anything electronic with a switch mode power supply.
Precisely. And why do these loads get special negative treatment for the neutral?
Yeah, why? They might even be perfectly balanced across the phases.
It might be balanced in terms of power, but they completely mess up the current waveforms. See, traditional loads draw current smoothly following the AC sine wave. Nonlinear loads, they sip power, then take big gulps only at the peaks of the voltage waveform. This creates distorted current shapes, rich in harmonics.
Harmonics, okay.
And the trouble is, on a three-phase, four-wire system, the normal phase currents are 120 degrees apart and should cancel out in the neutral. But certain harmonics, particularly the third harmonic and its multiples, ninth, 15th, etc., caused by these nonlinear loads, they don't cancel out. They actually add up in the neutral conductor.
Oh, wow. So you could have a situation where the neutral is carrying more current than any of the phase conductors, even if the load seems balanced.
Absolutely. It happens all the time in modern office buildings or data centers. That's why reducing the neutral size based on that 70% rule is strictly forbidden if those loads are present. It would be dangerously undersized.
All right, we've hammered ampacity and heat, which is mostly about safety, preventing fires. Now let's talk voltage drop. This feels more like performance and efficiency, right?
It is, primarily, although severe voltage drop can cause equipment malfunction, which could become a safety issue indirectly. But yes, mostly performance, making sure motors run properly, lights don't dim excessively.
And the code sets limits here, too, based on the nominal supply voltage you said, not the equipment rating.
That's right. Rule 8102 is the main one. If your supply is, say, 240 volts nominal, you use 240 volts for your voltage drop calculations, even if the motor nameplate says 230 volts.
Okay, so what are the magic numbers, the limits?
There are two key limits. First, the total voltage drop all the way from the supply point, like the utility transformer or main service disconnect, to the final piece of utilization equipment. That total drop cannot exceed 5% of the nominal supply voltage.
5% end-to-end. Got it.
But then there's a second limit that often catches people. The code further restricts the drop allowed in just the feeder part, or just the branch circuit part, to a maximum of 3%.
Ah, so that 5% total isn't just a free-for-all. If I use up my full 3% on the branch circuit, feeding a motor,
Then you've only got 2% left for the feeder supplying the panel and the consumer service conductors before that feeder even starts.
wow, okay. So that really forces you to think about the entire system. You can't just design the branch circuit in isolation. That 2% limit on the service and feeder side is pretty strict.
It is. It pushes designers to keep those main runs appropriately sized, especially if they're long.
Now, how do we actually calculate this? I know it involves conductor length, current, and resistance. The code uses something called K values in table D3, right? What exactly is a K value?
Think of K as a standardized resistance value. It represents the AC resistance in ohms of 1,000 meters or 1 kilometer of a specific conductor size made of either copper or aluminum. Crucially, the K values listed in Table D3 are based on the assumption that the conductor is operating at a temperature of 75 degrees C.
Okay, but hold on. We just spent all that time talking about how conductor temperature changes based on load and environment, and resistance changes with temperature. So is the 75 degree C K value always right?
Excellent point. No, it's not always right. It's a baseline. Remember, current flow causes heat. Heat increases resistance. So if your conductor is actually operating at a different temperature, you need to adjust that K value. It's this thermal correction loop.
How do we adjust it?
Table D3 has notes for this. If your conductor is likely operating cooler, say at or below 60 degrees C, maybe it's lightly loaded, its resistance will be lower than the 75 degrees C baseline. So you apply a correction factor of 29.5 to the K value from the table.
Makes sense. Lower temp, lower resistance.
Conversely, if it's running hot, maybe pushing close to its 90 degrees C insulation rating, its resistance will be higher. In that case, you apply a correction factor of 1.05 to the K value.
So multiply K by 1.05. Okay. Ignoring that could lead you to underestimate the voltage drop on a heavily loaded circuit, right?
Definitely. You might think you're okay, but the actual drop could be higher, potentially violating that 3% or 5% limit once it heats up.
Are there any other sort of special cases for voltage drop we should mention?
A couple stand out. Emergency lighting systems, specifically remote DC lamps fed from unit equipment like battery packs. Rule 46306 limits their voltage drop to a maximum of 5%. That's a total drop limit for that specific circuit.
Okay, 5% for emergency lights.
And then there's a niche rule for extra low voltage DC circuits. Note 4 in Table D3 allows you to apply a correction factor of 0.86 to the K values, making the calculated drop lower. But only if the load on that circuit doesn't exceed 2/3, 66.7% of the conductor's ampacity listed in the 60° C column of Table 2. It's an optimization for lightly loaded, low-voltage DC runs.
Interesting. And one more thing, dwelling units,
Mm.
homes. The code tries to simplify things for common circuits there, doesn't it?
It does, thankfully. For standard 120-volt, 15-amp, or 20-amp general-use branch circuits in houses or apartments, you don't always have to do the full voltage drop calculation. Table 68 gives you pre-calculated maximum circuit lengths. For instance, it tells you that using 12 AWG copper wire on a 15-amp breaker, you can run that circuit up to 60 meters before voltage drop becomes a concern.
That's handy. Saves a lot of calculation time for standard wiring. But it doesn't apply everywhere.
No, there are exceptions. Specific circuits, like kitchen counter receptacle circuits, which tend to have higher loads, are excluded. For those, you still need to run the numbers yourself. Hashtag tag, 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 outro. So when you pull it all together, what this deep dive really highlights is that conductor sizing. It's this intricate balancing act, isn't it? You're constantly juggling safety and heat management that's ampacity, degenerating termination temps with performance and efficiency, which is where voltage drop comes in.
Absolutely. And the code gives you these incredibly specific tools. Table 5A for ambient temp, 5C for bundling, D3 for voltage drop, K values, and so on to handle all these different variables based on the exact situation.
The precision is necessary because the physics is precise.
Right. And that level of required specificity, it really drives home how essential this knowledge is. We mentioned earlier, for instance, that the ampacity ratings for larger underground conductors, bigger than 10 AWG, they really depend on specific installation rules found in diagrams D8 through D11, things like burial depth and spacing between conduits.
That's correct. Those configurations are critical for allowing the heat to dissipate properly into the earth.
Okay, so here's a final thought for you, the listener, to sort of chew on. We know how critical managing heat is, both above ground and underground. We've seen the detailed rules for spacing and depth for those buried cables. So what kinds of unexpected, maybe long-term problems, particularly thermal issues that could force you to effectively lower the ampacity, might pop up if that required spacing or burial depth gets compromised during installation? Maybe the backfill isn't right or the conduit shifts slightly. How much does that real-world imperfection impact the theory the code is based on?
Yeah, where does the careful calculation meet the sometimes messy reality of construction? It's a really important question about avoiding premature conductor failure down the road.
Something to think about next time you see a trench being dug.
Indeed.
All right, until the next deep dive,